Hi, everyone. Um, I'm Han, from a PhD candidate from MIT CSIL, and the topic I'm going to talk about today is the sound of pixels, cross-modal machine learning between vision and sound. The first question is, what is cross-modal machine learning? For humans, we have sensory inputs such as vision, audition, and touch. And the goal of our group is trying to bridge the gap between these different sensory inputs and to let them learn from each other. Let's take a task of sound recognition, for example. The sound recognition task is given an input waveform audio. The goal is to recognize the objects and the events in the audio.
Good one. Oh, pretty boy.
We adjust the volume a little bit? It's a bit too loud. Yeah, and for example, this is a dog barking.
Dear Gordy, happy birthday to you. Hooray!
Oh, thank you. Yep, and this is a quite straightforward task, right? Like you're like given the audio, you're trying to predict an object or event. And in the deep learning era, you may say, okay, to solve this task, I just need to label a lot of data and then train a deep neural network to solve this problem. But we're lazy, we're not willing to annotate a lot of data. So what can we do? We can do cross-modal machine learning. 2 years ago, my lab mates downloaded a lot of millions of unlabeled videos from Flickr and YouTube. They look like this. These are all unlabeled videos with audio. And what we did was we take those unlabeled videos and design a learning scheme so that a sound model can learn from the vision. Let's see. From the video, from the unlabeled videos, we take the RGB input frames and feed them into already pre-trained vision networks. The vision networks will give you the object distribution and the scene distribution. And then we design a network for sound called SoundNet. It takes the waveform of the audio and outputs the object distribution and scene distribution that is predicted by the vision output. So basically, the sound network is learning from the vision networks. So let's see what the SoundNet can do.
Good one. Oh, pretty boy.
The SoundNet is only taking the audio as input, and the video here is only just for us to check the results. And the text in red are the predictions of scenes from the SoundNet, and the text in blue are the object predictions. You can see that for the scene, the SoundNet predicts pasture, yard, lawn, well, pretty much correct. And the object, it predicts three species of dogs. Because only from the sound, it's hard to tell which kind of dog it is. But it predicts 3 kinds of dogs, and okay. So the other example.
Dear Gordy, happy birthday to you. Hooray!
From this happy birthday song, the SoundNet predicts it could be a restaurant, a coffee shop, or a bar. It's an okay prediction. And for the object, it predicts candle, restaurant, and a torch. Something interesting is that candle is something that cannot be heard, but the SoundNet has the superpowers to see the candle. And compared to traditional supervised learning approach, because SoundNet learns from a lot of videos, so it outperforms a lot of previous approaches. And apart from sound recognition, we are also looking at a lot of different tasks in sound understanding. For example, this one, sound source separation. In music, people are usually like to separate instrument soundtracks from from a music, and also maybe separate vocals from it. And in the speech recognition, the sound source separation task is also known as cocktail party problem. In the cocktail party problem, like people are trying to separate the speech from each speaker and also to denoise the background of the speech. Another interesting task is called sound source localization. Like the goal is basically to recognize where or what the sound is coming from. Like, you know, a lot of home speakers like Alexa and Google Home are already using these techniques. And in our project, we are trying to solve these two problems simultaneously. And the paper title is called The Sound of Pixels. And our demos we already have the interactive demo at the link shown below. But I can show you these demos here for an input original music video like this. A user can click on one object and hear the sound it makes. If you click on the trumpet, and if you click on other objects that do not make sound, it's basically silent. Here's another example. It's a very beautiful piece of music, and if you click on the sax, and click on the guitar, and the background doesn't make sound. So basically, what we are doing is called something like simultaneous sound localization and separation. And all the learning is self-supervised and does not rely on human labeling or annotation. And here is our approach. First, we downloaded a lot of music videos from YouTube. There are more than 20 kinds of commonly seen musical instruments and more than 1,000 solos and duets pieces. Here are some samples. All these videos come with the music, and what we did was we mixed them together, and you get something like this. And then the source separation task is to go from this mixture and back to the three components. So if we do it in an audio-only approach, it will be an ill-posed and very challenging task. And also, you will meet permutation problem if you do it in an unsupervised way. So in our project, vision is to rescue. If we treat our system as a black box, and the input to the black box is the mixture audio and a video of interest. So if we input the video of the violin, it should output the sound of violin. If we input the video of an accordion with the mixture, it should output the sound of the accordion. The same way, if we input the video of flute and the xylophone, and it should output the sound of those. So the key ideas here is that vision and sound serves as each other's supervision during the training, and the visual feature works as a sound filter, works like a sound filter that extracts the sound of interest. And we'll go into some details. Basically, our network is composed of a video analysis network. This video analysis network taking the video frames and to extract the features, and finally with a max pooling to get a k-dimensional video feature. This is the video analysis network, and we also have an audio analysis network. The audio analysis network takes in the audio waveform as input, turning to a spectrogram with a Fourier transform, and then to go through a network to extract the audio features. And the last block is an audio synthesizer network. The synthesizer networks takes in both the video features and audio features, and to fuse them and do a fusion, and finally predicts an audio mask. This audio mask will mask on the input spectrogram, and then we do an inverse Fourier transform to get the sound of interest. Here's an example, a training example. We mix the three sounds together. We show the spectrogram here and their mixer, the spectrogram of the mixture. After mixing, and our model taking the video input as well, and predicts 3 masks based on the video. Those masks will be masked on the input spectrogram to get the output spectrogram. And these output spectrogram, we can compare them with the ground truth. You will see that pretty much similar. For the sake of time, I won't play each of them, but just from the spectrogram, you can tell that the output is very similar to the ground truth. And at test time, how do we do the sound of pixels? How do we get the sound of pixels? Basically, we remove the max pooling layers at test time, and instead let the users to click on the pixels and extract the features of the pixel and use that features, the pixel features, to produce the sound. Okay, and now that we are able to get the sound of each pixel, so here we do some visualization. There are, we can visualize the volume of each pixel. It's basically, for each pixel, we measure how loud it is, and then and plot them in the bottom row. The heat map the red part of the heat map shows the high volume in this video. You will see that the instrument has high values, and means that they are making sounds. And the second visualization we did was to see what sounds that each pixels make. Like, what we did is, like, for the sound of each pixel, we do an embedding, and then and project them into the color space. So at the bottom row, different colors means the different sounds from the pixels. And you will see that how the sounds cluster together. Basically, 2 instruments in the same video that makes different sounds are shown in different color. And there are also something interesting about the network. We visualized them and found that because of our design, there are corresponding channel activations. That is, a single neuron can be responsible for a specific semantic concept. For example, we found that channel 6 in the network is a violin detector. And this violin detector, in the vision, it localized the position of these violins. And in the audio network, it activates to the harmonics, the high-order harmonics of the violins. And channel 11 is a guitar detector. This detector detects guitar in the vision, and in the sound, it activates to the low-frequency part of the guitar. And channel 14 is a xylophone detector. It detects xylophone, and also on the spectrogram, it has its very special patterns. And I have more examples to show here. You click on the piano. and the face does not make sound. If you just click on the drums. Click on the piano. What can the technology be used for? Like here are some simple applications we have thought about. It's like remixing. Given a music video like this, it's a non-professional user. You want to edit this music video, and what you can do is simply extract the sound of each instrument and trying to remix them. You can do something like this. For example, you turn up the volume of the flute. And you can turn down the flute and turn up the xylophone and do some simple remixing. And I think this will be a very useful tool for non-professional users and to edit their own multimedia files. Okay, and our paper is already published in ECCV, and we also have the project website. As I mentioned, you can play with our demos interactively. And any questions? Yeah.
I have two questions. So one is that most of or pretty much all the videos
Yeah.
have two sound sources.
Sure.
Does this generalize to like more than that?
Yeah, actually, we tried with a different number of sources. It's whenever, currently it works fine with 3 or 4, but whenever it goes to above 5, it's very challenging. We think this problem, yeah, should be addressed. But actually, we also look into the real-world cases. There are very few people like is able to separate the sounds of like more than 4 or 5 sources. But yeah, I think this is still a challenging thing, and we're trying to address that.
The second one was that, say like the sound source wasn't moving, like in the video, like it was just
Sure.
like from a radio or something like that. There's no activity. And so the salient map, when we actually, it wouldn't pick up on it, right? And so it would actually get localized the sound.
You mean if the things are moving, or?
If it was just like a still, like, a video, but it was just like a radio or something like that, there's no activity to that. It was like the radio's like playing audio.
Okay. So, sorry. You're saying like?
I guess I'm playing like,
Sure.
there's some kind of bias because like the video, there's actual people doing some kind of activity, and perhaps like the frequency at which particular activities or the salient map is on particular activities, it's a little bit easier to match with the sound. So like in the case where the video is just like a speaker system or something like that, there's no person in it, but it's playing audio. Would this still be able to, when you click on the image, would still be able to localize it to that particular subject?
Yes. I think it's possible. Yeah, but we show some simple, examples. I think that could work. Of course, like we need like better video analysis network. Basically, we extract better video features and audio features, and that I think that could work. Yes.
So it seemed like when I listened to the video you showed about with the drums and the piano player together, there seemed to be like more noise in the separated sources.
Sure.
So I was wondering like whether specific cases you noticed when testing whether your model worked better, like specific types of instruments or sounds like.
I think for the types of instruments that have that their frequency band is very narrow, that works better. For example, piano is very challenging because for the piano you can play almost all the notes and that's a very challenging part. It's a very challenging instrument. And the easy ones, I think, are those, for example, violins. And in the spectrogram space, if you look at the violins, actually they have pretty narrow band of frequencies, a pretty much high frequency part. So this is something easy. Yeah. The string instruments are generally much harder. Go.